Hi, everybody. Welcome to the August 2023 SJAA Imaging SIG meeting. And today we have Ed Beshore, who was the Deputy Principal Investigator of the OSIRIS REx mission, and he's going to tell us all about it. So take it away, Ed.
Okay, I'll start by sharing my screen here and making sure that I have my sound shared. Okay. Is that coming through?
Yes, it is.
Okay, well, hi, thanks very much for asking me to be here tonight. It's always fun to talk about this mission and the fact that it's only about 30 more days or so before it's over. It makes it all the more timely. I think I'll start by just telling everybody a little bit about my own experience. I actually started out as an amateur. I was in the computer industry through the 90s. And I had a business that afforded me the opportunity to build a telescope in my backyard in Colorado. So I had first of all, a 10-inch Meade, then a 14-inch Celestron, and I've got a 6-inch astrophysics refractor now. And I was having a lot of fun with it. I did some work with the Center for Backyard Astrophysics, a group that was doing some citizen science work. I was doing photometry, and I was having such a ball that I asked my wife, who, by the way, has a degree in optics, so it made it really easy to buy a lot of this stuff. But I said, I really need a bigger telescope. And she said, your grant committee has cut you off. You need to find somebody who has a bigger telescope and go work for them. And so I took her seriously, and I went back to my alma mater at the University of Arizona and looked up a friend of mine who was starting the Catalina Sky Survey, which is a near-Earth object survey looking for hazardous asteroids that might hit the Earth. And I had automated my telescope in my backyard so that I could keep my day job and let the telescope run at night and do the analysis. And then I could just gather the data and do a little bit more work on it and send it in. And the folks at the Catalina Sky Survey needed the same thing done. At the time, they just had this telescope in the lower right-hand corner, which is a 1-meter Schmidt camera. And they had just put a 4K by 4K CCD on it, back illuminated. It was pretty hot stuff, and was already beginning to put their eyes on an unused 60-inch reflector at the top of Mount Lemmon outside of Tucson, Arizona. That's the telescope that's on the left. So all of our telescopes at the Catalina Sky Survey are telescopes that had fallen into disuse and allowed us to basically get unlimited amounts of time on them. And so we retrofitted them, put these 4K CCDs on them, and then did the same thing with a telescope at Siding Spring, Australia, on a half-meter Schmidt telescope, which is in the foreground of the picture on the upper right-hand corner. So effectively, I had taken what I'd learned as an amateur and turned that into becoming a professional. And ultimately, I was head of the Catalina Sky Survey for several years. When the opportunity came along for me to become the deputy PI of OSIRIS REx in 2012. The job there was quite a bit different. I had learned quite a bit about technical management. And so my job was to manage the science team. And the picture at the bottom is our science team. And what made our science team different than most missions, missions are typically like the science team stands down until the spacecraft gets put wherever it's supposed to go. That means if you're going to orbit around Mars, they get you into orbit around Mars, they get a nice stable orbit, they make sure they check out the spacecraft, and then they turn it over to the science team and say, have a ball. OSIRIS REx was very different because we were relying on the science team to actually produce products that were necessary for the conduct of the mission. We needed to produce the topographic maps so we could put the spacecraft down in the right place to get a sample. So we really had to organize our science team to become an operational part of the mission. And that was really what my job was. The spacecraft is up in the upper left-hand corner. I'm the guy in the middle bunny suit. And then I always like to show people the whiteboard on the right, because that was my to-do list as the PI. I was responsible for all sorts of the subsystems and monitoring that sort of thing. But in addition, keeping the science team going. Now, the way NASA runs missions, as I was explaining to Hai a little earlier, if you grew up, in the 60s, you probably knew that as you started out with your family, maybe you'd go out and buy a Chevrolet, and then someday you might get a Pontiac or a Buick, and then ultimately, if your career really worked out, you'd get a Cadillac. Well, NASA has the same approach towards missions. They have what they call discovery class missions. At the time, those were $600 million plus the rocket, or rather, I should say, including the rocket. Our mission was the Buick. It's what's called a New Frontiers mission, and New Horizons, which is the spacecraft that went to Pluto, was a New Frontiers mission. Those typically were cost capped at around $1 billion, including the rocket. And that cost cap also includes reserves. So we had to maintain about 200 million in reserves because NASA knows that when you do this stuff, you end up having to spend money you didn't plan to spend. And they've gotten quite good at planning how to lay that sort of thing out so that they don't have to go back, or we don't have to go back and ask for more money later on. At least that's the way it works with the Discovery and the New Frontiers missions. Then they also have, the flagship missions, and that's the missions like the rover that's on Mars right now. And those are typically run directly by NASA. And those are very expensive, oftentimes running several $1 billion. So that's a different class of mission. But we would partner when we put the mission together. We partnered with Lockheed Martin, who would develop the spacecraft. So the picture on the left is taken at the Lockheed Martin High Bay facility as the spacecraft was coming together. And then we also partnered with NASA's Goddard Spaceflight Center, because NASA supplies a ton of expertise when it comes to putting missions together. They supply the systems engineering, they help out with all the risk management, and of course, they know how to buy a rocket, and they know what to do with it once they've bought it. So that's something that was beyond our ability as a university run principal investigator-led mission. So we'll start out here with the next.
4, 3, 2, 1. And liftoff of OSIRIS REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Firing look good. Starting to need pump speeds and check pressures over the family. Some read chamber pressures have.
So we had this picture-perfect liftoff on September 8th of 2016. We were on an Atlas, what they call 411 rocket. We had one solid rocket booster on the side, and everything just went beautifully. If you've ever watched a launch from Cape Canaveral, oftentimes it's insufferably hot and humid. The mosquitoes can be terrible there. But it was not like that at all on this day. We had this beautiful onshore breeze, and it was just a picture-perfect launch. Spacecraft worked great. We did several deep space maneuvers in the weeks following the launch in preparation for an Earth gravity assist to get us to the object that we were headed to, called Bennu. All of these missions start with thousands and thousands of requirements. But all these requirements all sort of work upwards to these basic mission objectives. So all of the requirements of a mission really can be traced to these top-level objectives of what you want to accomplish with your mission. And the top-level objective for us, the principal objective, was to return and analyze a sample of a carbonaceous asteroid, and enough of it to study the nature of its history in the solar system. The whole idea here is that if we went to a primitive asteroid, we might very well find materials that were relatively unprocessed since the beginning of the solar system. And we're really trying to address some of the basic questions of where did water come from? That is really not a solved problem at this point, although we're starting to get a better sense of things. And we thought that by bringing back a sample of a carbonaceous asteroid, which is the most primitive type of asteroid, that we might be able to actually answer some of these key questions. I like to show this picture of NGC 3603 because it's really quite extraordinary. It was taken with the Hubble Space Telescope, but it shows actually some of the key phases of evolution in one image. So you see these hot blue white stars in the center. They're burning up their fuel really rapidly. They are generally quite massive. That's why they burn their fuel so quickly. And eventually they become unstable and they create supernova. And there's actually a supernova remnant just to the about 10 o'clock from the cluster in the middle. And you can see a ring around it, and you can see two polar outflows on either side of it. And it's injecting into the interstellar medium all this material that was synthesized during the supernova. That material then begins to reaccumulate under the force of gravity, and then eventually you get these little concretions. Sort of, if you can see that, I'm not sure if you can see my arrow, but right there. And if we look at closer, you start to see that these are probably primitive protostellar disks. And that's really the nature of our early solar system when it formed about 4 billion years ago. And we really would like to get material that was as close to that time in the history of the solar system as we can. Fortunately, telescopes like the Webb have really transformed our understanding of how these things work. And we're actually taking pictures now of protoplanetary disks, which are showing gaps like our asteroid belts. And we're actually starting to see even condensations in these clouds that may be planets starting to form, which is this is just kind of an aside, but it's just such a fantastic image. I had to show it tonight. We also had some other requirements that we wanted to fill. One of the big questions is, where do near-Earth objects come from? Because near-Earth objects, the ones that might hit the Earth, really actually have a fairly short dynamical lifetime. One of the three things happens. They either get thrown out of the solar system through a close gravitational encounter with a planet, they fall into the sun, or they hit a planet. And of course, hitting a planet is what we're concerned about. But the problem is that after about 10 million years, if you just inject a bunch of NEOs into the inner solar system, after about 10 million years, they'd all be gone. So something is continuing to replenish these. And we think that the reason for that is something called the Yarkovsky effect. And this animation shows what happens. An asteroid out in the belt is getting warmed up. That warmth is re-radiated and acts like a small rocket thrust. And depending on the direction that the asteroid is rotating, it can cause the asteroid to move inward towards the inner solar system, or it can cause it to move outward, depending on which way it's rotating. So the Yarkovsky effect is one of these things that takes place over millions and millions of years, but with this very small radiative thrust that's occurring, it can completely change orbits. And that is something we wanted to investigate a little more closely. In addition, we wanted to do some other important things. We wanted to compare Bennu's, that's the asteroid we went to. We wanted to compare its global properties with our ground-based collection of asteroids, which are meteorites. We wanted to look at the global properties of the asteroid, the chemistry and mineralogy, to understand a little bit more about how Bennu formed. And we wanted to understand the spectral properties of at the sample site, because we wanted to get really good context for our sample. We wanted to be able to say, when we brought that sample back, here's everything we could find out about the place we got that sample from. So those are the key mission objectives for the OSIRIS REx mission. When we started to decide where to go, we knew at that time, this was about 2008, there were probably around 500,000 asteroids in the catalog that we knew about, that we had orbits for. About 7,000 of those were near-Earth asteroids. And we wanted to go to a near-Earth asteroid because they come to you and you don't have to go to them. And that means that has a lot to say about how expensive the rocket is that you're going to send your spacecraft out on. So it's much easier to go to a near-Earth asteroid if you can find the right kind. And there were about 192 of those that had optimal orbits for sample return. So not only do you have to get to the asteroid, you got to get back from it. and you've got to be able to carry enough fuel on your spacecraft that you can actually have a trajectory that's going to get your sample back to the Earth. The other thing that was important to us is we wanted an asteroid with a diameter over 200 meters, because most smaller asteroids tend to spin rapidly. And we thought that we probably, with a rapidly spinning asteroid, it might have thrown off any sampleable material into space just by centripetal force. And so we wanted a large enough asteroid that it could actually hold together enough and have some loose material on the surface that we could bring back. And we wanted it to be one of these carbon-rich asteroids, one of these carbonaceous asteroids, because we believed those were representative of what the inner solar system was like when the solar system was formed. So we chose Bennu, and we were lucky to be able to get some radar imagery on the spacecraft using the Arecibo telescope in Puerto Rico. Rest in peace. It was, this is on the data on the left is the kind of data you get back from these radar observations, and you get a whole series of these images, and you can deconvolve them to actually produce a shape. So the object on the right is the shape that was derived from the radar observations. In addition, radar allows you to get extremely good orbits on things because you get range information, and that's not something that you can get with normal astrometry.
How accurate was that shape?
Actually, quite good. You're going to see an actual image of Bennu. So yeah, have a look at that. You see that there's this equatorial sort of looks like a walnut, and there's this equatorial material that has probably migrated from the poles towards the equator because of the rotation rate of Bennu and the fact that the surface is probably not very cohesive, and so material can move around on it. It's about 500 meters in diameter. We thought the surface was smooth. There was a discernible 7.5 meter feature on the surface. And the data that we could get from radar suggested that it was probably loose material there. And we also did light curves with conventional photometry, and that suggested there were no satellites in orbit around the asteroid. So we thought that that it probably was not a hazardous environment to be working in. So we put together a series of instruments that flew on the spacecraft. The most important one is the camera suite, and that was built here at the University of Arizona. We had a zoom lens, we had a wide angle lens, and then we had a specialized camera to image the sample event. And these were all built here and were operated through an internally redundant single module that controls all those cameras. In addition, the Goddard Spaceflight Center built OVIRS, which was a visible and near infrared spot spectrometer, which was good from about 0.4 microns out to 4 microns. And that was really important for allowing you to determine mineralogies and compositions. So we would put together a spectral map of the entire asteroid to try to find a spot that was interesting from a chemical point of view. The Arizona State University built a thermal infrared spectrometer that was good to about 5.7 out to 50 microns. So that's very much thermal. And what you can do is you can actually measure the way heat moves through the surface and tell something about the cohesiveness of the surface. I mean, think about standing on a rock that's been exposed to the sun all day, as opposed to going to a sandy beach where you dig your feet in a little bit. It's hot on top, but you dig your feet in a few inches and it's cool. The reason it's cool is because all those little sand grains are touching each other just at little spots. They're not connected to one another. Pardon me. And so the thermal conductivity between grains is not particularly good. So you can actually say something about cohesiveness by looking at the thermal data. We also had a dual laser scanning LiDAR system that was going to be used to generate a topographic map. And that was a contribution from the Canadian Space Agency. The spacecraft was a sister spacecraft to a mission called MAVEN, which flew to Mars. We looked just exactly the same as MAVEN, except our solar panels were different. We're basically a set of carbon fiber trusses attached to a big hydrazine tank. And so that hydrazine tank is in the middle. The rockets are all on the bottom. There's a lot of cameras and so forth attached to those panels. And then on the top deck is what we call the science deck. And that's where you'll find all the cameras that I just talked about, as well as the sample return capsule, which you see in the middle here, which is going to receive the sample after it's been retrieved. And then a large communications antenna on the side. Pretty simple stuff, from the standpoint of the construction. That I was actually kind of shocked to see how sort of put together it was. Just hang a bunch of instruments on the side of these panels, and off you go. So we did do an Earth gravity assist. The reason we needed to do that is we actually needed to change the plane of the orbit. It's pretty low energy to get out to Bennu, but Bennu's orbiting in a different plane. And so you'll see right here that by going by the Earth, we actually changed our plane into the plane of Bennu. Plane changes, inclination changes rather, are pretty expensive from an energy point of view. So that's why you want to be able to do an Earth gravity assist to get that assistance. So eventually we got out to Bennu. And I'm not going to go into all the details about what we did around the asteroid, but to give you an idea of what you can do around a small asteroid, this is an example of the kinds of maneuvers that we did around the asteroid to get information at different solar angles. We're just sort of bombing all around all over the place, trying to get different solar phase angles, which is important for spectroscopy. It's important for topography to try to get shadows. And you can do this real easily around a 500-meter asteroid because you're not really fighting its gravity. It's really just you're just out there flying around anywhere you want to go. Now, to catch the sample, it was a really great approach to doing this. We didn't want to have a lot of moving parts. And so we have this thing that looks like a air filter off of a Pontiac that basically is attached to nitrogen bottles. And we're going to touch that down on the surface of Bennu. So here's a test. We touch that down on the surface of Bennu. We release the nitrogen, and we push the nitrogen through that filter, and it activates material on the surface. So you see that. It goes through a little plastic flap there, and it catches that material on its way out. So no need to bore a hole, no need to attach yourself to Bennu. I mean, we didn't really want to land on Bennu. We just wanted to touch it because trying to land and get yourself attached, that's really hard to do. So the idea is if you have enough loose material on the surface, in theory, we should be able to capture a bunch of material. So in space, this is the way it would look. We would extend this out on the arm, and we would orient the tag head, we call it touch and go head, and then slowly maneuver down towards the surface where we would touch it, release the nitrogen, and then we would have this novel system of how we would weigh it. We would spin the spacecraft before we went down to the surface, and then we would spin the spacecraft after we got the sample and measure the change in the amount of energy required to spin the spacecraft, and we could weigh the sample that way. So we could get an idea of how much sample we had, because we really wanted to get 60 grams. 60 grams would give us about 25 grams for immediate analysis, and also about 35 grams that could be archived for future investigators using techniques that we know nothing about yet. That's what's been so wonderful about the lunar samples, is we're now applying techniques of mineral analysis to those samples that back in 1969 we had no idea would ever exist. So just very quickly, the navigation challenges around an asteroid like Bennu are considerable because the mass is so low. The mass of Bennu is about 10 to the minus 14th that of the Earth. And the forces that the spacecraft feels from solar radiation pressure is about the same as it feels from the gravity of Bennu. That makes all of our orbital maneuvers very small. Some of our delta V's were only 1 centimeter per second. And it's very hard to build rockets that give you exactly 1 centimeter per second. So you have a lot of maneuvering uncertainty that you have to be careful about. And you have other sources of these, what are called non-grav accelerations. You've got solar radiation pressure. You've got albedo from the asteroid. The asteroid's reflecting heat, and that is hitting the spacecraft, and that is actually causing your spacecraft to move around. You've got outgassing of spacecraft components. The spacecraft is re-radiating energy that it's absorbing, and then these uncertainties in orbital maneuvers. All of those add up to producing a real headache for our navigators. And so this third bullet, in orbit, the along track drift that we would get due to these non-gravitational forces would produce uncertainties in the spacecraft state that were considerable after just 3 to 5 days. So what that means is that you can't just put the spacecraft in orbit around Bennu and turn your back on it, because in 3 to 5 days, you won't know where you're at, and the spacecraft won't know where it's at. You've got to either have some sort of onboard navigation system, or every day you've got to be taking these navigation, well, we call them OpNav images, where we're basically taking images of the asteroid to figure out where are we, and then making navigational adjustments. If we just let the spacecraft go, eventually its orbit would take it straight into the asteroid. So you just can't turn your back on these low mass objects. And one of the pioneering aspects of this whole mission actually was developing a lot of the techniques for maneuvering around these very small objects. So we had to produce really good topographic maps because we were using those for dead reckoning around the asteroid. And I'll tell you a little bit more about that in a sec.
Can I ask, so
Sure.
I assume that the spacecraft is not doing this navigation, that it's just you're doing it here on Earth and sending it back?
Yeah, when you're in orbit, we're basically taking OpNav images, transmitting those back to the Earth, analyzing it, figuring out where we're at, and then making navigation adjustments. But during the descent to the surface, the spacecraft's all on its own, because we had on the order of 6-minute round trip light times, and so that's just too long. We couldn't, live stick that spacecraft down, from the Earth. We had to basically, train the spacecraft to figure out where it was at and get down to the surface all on its own. So ultimately, we would leave no sooner than March of 2021 and no later than June of 2021. And we have an arrival coming up on September 24th at the Utah Test and Training Range outside of Salt Lake. This is an area where we've landed sample return capsules before. It's just a big empty area, it's a test area. And so it will come in at about 7.5 miles per second, just like an Apollo capsule. We have an ablative heat shield on it. And so it's using very much that similar kinds of technology to get down with what we hope is a soft parachute landing. The spacecraft will be the sample return capsule will be rapidly gathered up and flown to a curation facility at the Johnson Space Center. So that's the same place that manages the lunar samples. And then they have about 6 months to inventory the contents of the sample return capsule. And then we'll take requests for loans of material to any qualified institution around the world after they've got that inventory. So essentially the first thing they'll do is build a card catalog, and then you can start checking out samples. So that was kind of, where we're at as of the launch. Now, one of the things I would put up at every science team meeting is this first line: planning is everything, plans mean nothing. And there's a lot of variations on that, and what it's effectively saying is it's really, really important to make all your plans, but you don't want to get too wedded to them because reality steps in and changes what you need to do. Hopefully your planning process, though, has prepared you for that. So the first thing we discovered, so we got a lot of surprises on the mission. The first thing we discovered is that Bennu was launching rocks at us. We started taking some of these images, and this has been highly stretched, so you can see over to the left some of these objects that are getting wafted off the surface, and in some cases into orbit around Bennu. In some cases, they were just flying, a ballistic trajectory and landed back on the surface. At first, we didn't know what was going on. Now we believe that this was probably because of the low gravity of Bennu. This is thermal fracturing of the rocks because Bennu gets very hot. It's close. It's like Earth. It gets very close to the sun, and it gets very cold because it rotates in about 4.5 hours. So that repeated freeze-thaw cycle, or the cold heat cycle, occasionally will fracture rocks, and that's enough to make them pop and fly off the surface of the asteroid. Of course, we were really concerned about whether this was going to be a problem for the spacecraft, but after looking at it, carefully monitoring what these things were doing, we found that the delta V between our spacecraft and these objects was very small. And so we probably could handle a collision if we had one, but even then the likelihood was probably going to be low. There were 3 distinct cycles of this where we saw this happen, but there you go. There was one of the first surprises that we had. The other thing is that Bennu was rougher than we expected. The only other asteroid that we'd been to, that mankind had been to before this, that we really got a good close look at, was Itokawa during the first Japanese Hayabusa mission. And this is a picture of it. It's roughly about 500 meters along the long axis. It had some smooth areas, probably because this is probably a binary asteroid. So what we're probably seeing here is 2 distinct asteroids that are just touching each other over here at the sort of the 2/3 to the right, and probably moving around a little bit and creating some fine material that we're seeing. But we looked at that and said, well, there are some areas there that are pretty good size that we think maybe that lower, this area right down here around the bottom, if you can see my mouse, maybe we'll find something like that on Bennu. That's about a 50-meter radius circle. So we kind of use that as a defining point about how good we had to make our ability to land the spacecraft. We could put it down in a 50-meter radius circle. We felt like that Itokawa would be representative in that regard. Not so much. So this is, Hi, back to your question about, did our radar image look kind of like Bennu? It does. We obviously see a lot more detail here, but it was also much, much rougher than we expected. A lot of boulders, a lot of craters, a lot of very precariously oriented boulders. And it looked like we were actually going to have to put the spacecraft down in something along the size of 2 parking spots. So we really had to develop some additional new techniques for accurately and safely getting the spacecraft down to a spot on the asteroid. So what that meant is we needed a much better topographic map of the asteroid. Now, this is a representation of the map that was produced. It's actually stunningly beautiful. If you appreciate this sort of thing, you can actually download this map from NASA. It's 900 megabytes, 5 centimeters per pixel. It's the highest resolution topographic map made of another body ever. And we use this to create maps that we would load into the memory of the spacecraft, so the spacecraft could take pictures on its way down and figure out where it was and determine whether it was on track to the sample site. Really quite spectacular. It's a lot of fun actually to look at this image in high resolution because the resolution is stunning, and this is made of hundreds and hundreds of independent images, and all the shadows have been matched up. So you don't see seams from shadows and that sort of thing on it. It's really just a beautiful piece of work. So this is an image, actually an image. This is an animation made from that topographic map. So this is not imagery. This is animation from that imagery of ultimately the place where we decided to go and get a sample. This is called Nightingale Crater. It's about 20-meter radius. And you can see that there are some really large boulders around there. We needed to be able to put down right in the center of this thing. You know, so it was quite a hazardous area, but it looked very interesting from a scientific perspective, and also looked like there was a lot of sampleable material there, fine material that we could pick up with the spacecraft. So, by the way, I'm going to give you a link to a NASA site where you can get about a 5-minute tour of Bennu with this technology. It's quite nice. That topographic map allowed us to make some really beautiful animations. So when it came time to actually do the sampling, you can kind of see this is another animation that was produced after the fact based on imagery from the spacecraft, as well as post hoc imagery taken of the sample site after the sample was taken. So we found out that Bennu was not cohesive at all, very loose material. We moved about 6 tons of rock over the course of just this short 20-second sampling event. We sunk almost a half a meter beneath the surface before we halted our forward motion into the surface. The surface is incredibly weak, hardly any cohesion at all. And what I mean by cohesion, it's, you know, what forces are keeping this stuff together? You know, the dust bunnies under your bed are basically stuck together due to van der Waals forces, little electrons just holding everything together. Well, that's about all that's holding Bennu together as well. And then this very weak gravity. So we did manage to get a nice sample, we think. But of course, there was another surprise. I told you about that process where we were going to weigh the sample head by spinning the spacecraft. Well, we got up and took a picture of the sample head, and it looked like that plastic flap that was supposed to close didn't close, and we were starting to lose sample. And so the last thing we wanted to do was spin the spacecraft and watch all of our sample go flying off into space. So we looked carefully inside the sample head as carefully as we could, and we decided that we must have gotten plenty of sample because it was stuck open. This plastic was stuck open, and we decided just to put the sample head away and get it safely tucked away so that we wouldn't lose any more material. So the last big question now is, how much sample did we get? You know, you can find out a lot about our mission from a special issue of Science magazine that came out in November of 2020, which will tell you pretty much everything we learned in orbit around Bennu. But we are still waiting to find out in about another month how much sample we got. We hope that we got at least 60 grams. We think some people have suggested we got about 1 kilogram, which would be spectacular if we got that much. And also, I referred you to that website where you can take a tour of Bennu from that high-resolution topographic map data, and that link is just at the top of the page there. So with that, I think I've probably talked myself out. I just say thanks very much for the opportunity to tell you a little bit about the mission, and if you have any questions, I'll be happy to take them.
Well, it's very, very interesting. I have a sort of a simplistic question. I've always had the fantasy that these things were sort of like dirty ice cubes
Mhm,
And, that they would be more cohesive
mhm.
than that, because if they're supposed to, I don't know, I really don't know if this is true or not, but I thought, if there's water in these things, it would freeze and then it would kind of amalgamate together more like that. Or is that a completely wrong idea about?
No, it's not a bad idea. It's probably more descriptive of a comet than it would be
Okay.
a near-Earth asteroid. The thing to remember is this asteroid has been coming close to the Earth for a long time, so it gets very hot. It's probably boiled off any surface water that might have occurred early on.
Mhm.
But on the other hand, perhaps deep in the surface, one of the things about these non-cohesive objects is there's lots of space in them, so perhaps there's some ices deep down. Of course, we won't know that with our mission, but what we're really looking for is water that might be bound up chemically in the minerals, and so that would tell us a little bit about the early exposure of the mineralogy of the asteroid to water early in the days of the solar system, probably when Bennu or its protoplanetary body that made Bennu up before a collision, that might have been further out in the asteroid belt. A collision might have happened. Bennu formed. The Yarkovsky effect brought it into the inner solar system and made it a near-Earth object. Because again, remember, as a near-Earth object, it can't have been here more than 10 million years. It would have hit the Earth, flown into the sun, or actually been thrown from the solar system.
Mhm. Very good. I had one other question. It has nothing to do with the first question, but I was just curious, in your career as a organizer of various observatories, what software did you use to organize the remote access to the observatory, or did you make it all home by yourself?
Made it all myself. That was my job for the first 2 years. I wrote this all. And now it's 20 years old. It's been modified a lot. There was really nothing at the time that we could use. We had a telescope control system; those were around. But even orchestrating the image taking with the slewing and the downloading, we needed to make sure that we kept the shutter open as much as possible, so we wouldn't just take an image, download it, then slew. We wanted to be slewing while we were downloading, just to make sure that we were as efficient as possible. So that was all custom. Today you probably could do it with some commercial products, or at least partially. But the image processing pipelines and so forth were all built by us.
Great.
Are there other questions for Ed? Well, Ed, I have a question. When you did your touch and go, like at what speed was the spacecraft approaching? And then a related question is, all those tons of material you blew off, was that blown off, by the nitrogen or by the propulsion trying to get off the surface, or what?
It was really the nitrogen. We went about a half meter deep and then blew the nitrogen. So it really just, it blew everything away, and it actually created quite a crater afterwards. In fact, we made the decision to go back and take a look at the crater just to see what we had done, because we thought that would tell us a lot about the cohesiveness of the asteroid. We had a tremendous number of arguments about what we would find as far as the cohesiveness, because that went to the whole issue of whether we'd be able to get a sample. We had some very, very smart people telling us it was going to be stuck together and hard to break up, and we had people telling us it would be loose, like we found. So there was a lot learned in that process. But yeah, that was all done by the nitrogen, which was it's actually a pretty energetic process. And we approached the asteroid on the order of, I believe the number was about 10 centimeters per second.
10 centimeters, so 4 inches a second, and it was navigating itself.
That's right.
I take it you got pretty close to your target.
Yes, we got 10 centimeters away from our target position. So that was pretty amazing. The navigators are really exceptional people. I have a huge amount of respect for what they were able to accomplish.
I assume that if you detect it, if the satellite, the OSIRIS REx detected it wasn't quite right, it could have just reversed course and tried again.
That's right.
Got fuel
Yep,
for.
yeah, we could abort the approach if at any time it took one of these op-nav images. So what it did is we basically built this model, this topographic model of the asteroid, and then we said to ourselves, now what will OSIRIS REx's navigation cameras see at any point along the mission? And so we could simulate what it would see, and then we could put those simulated images up on the spacecraft, and we could say, if it doesn't look like this at this point in the mission, stop and back up.
And that was done by camera as
That's
opposed to like LiDAR, like the self-driving cars do all that via LiDAR maps and LiDAR.
Yeah, we thought we would be able to do it with LiDAR, but we didn't actually. There were several issues that made it difficult with the Canadian LiDAR that we had. Turned out to be an invaluable instrument in itself, but to actually use it for the touch and go, it wasn't gonna be accurate enough.
All right, very cool. Are there other questions in the audience? Well, I guess we're all done.
All right.
So thank you so much, Ed, for this amazing talk, and we're looking forward to hearing more about what happens. So
That's right. Yeah.
Now, let me just ask you one last thing. It's just so hard to believe that it sits there and maybe I misunderstood, like no real news for 6 months, and then PIs will write proposals for.
Well, so we'll know how much sample we got. But the first thing that they'll do is they'll just start inventorying everything so that they can produce this list of samples that'll say something like, forsterite crystal, 3 grams, oriented this way. And they'll take pictures, and then you'll be able to get online, see all that, and go, that's what I want to look at. And then you'll make an application for
Okay. So in other words, the composition of the sample, like sort of what it's made of, will be published, and probably there's some science just in reading that and
oh yeah,
and saying, oh my God, right.
Exactly. Yeah.
All right. Well, thank you very much. And
You're welcome.
I'll end the meeting, and everybody please unmute and give it a big round of applause.
Very good.
Thank you, Ed, and thank you, Hi, for organizing it.
All right. Well, we'll see everybody next month.
All right. Take care. Good night.
Bye-bye.